We were wrong. For 30 years, we thought we had a pretty good picture of how our universe began. We had the timeline. We had the physics. We had the standard model. It was a beautiful, elegant recipe that explained everything from the first atoms to the swirling galaxies we see today. We were confident. We were comfortable. But then, we built a golden eye, launched it 1,000,000 miles into the dark, and opened it. And in a single moment, that beautiful story shattered. What we are seeing in the dawn of time is not what we expected. The baby galaxies are too big, they are too bright, and they are far too old. It is as if we walked into a nursery expecting to find infants, and instead found fully grown adults waiting for us. The story of creation has to be rewritten, and that is exactly what we are going to do today. Welcome to the most significant scientific detective story of our lives. We have discovered a body, a celestial anomaly that shouldn't exist, and we are using the ultimate forensic tool to figure out how it got there. This isn't just about pretty pictures of stars. This is about the crisis in cosmology. It is about the thrill of realizing that the universe is far more chaotic, fertile, and mysterious than we ever dared to imagine. Over the next hour, we are going to tear down the old textbooks and look at the raw, uncomfortable, and exhilarating data that is currently keeping astrophysicists awake at night. This is a journey that will take us from the high-stakes engineering labs on Earth to the very edge of the observable universe. It is a long road, but I promise you, by the time we reach the end, you will never look at the night sky the same way again. So, settle in, turn off the distractions, and let's go back to the beginning. To understand why this is happening, you first have to understand the machine itself. The James Webb Space Telescope, or its JWST, is not just a better version of the Hubble telescope. Comparing the two is like comparing a magnifying glass to an MRI machine. Hubble showed us the universe in visible light, the same light your eyes see. It gave us the what and the where. But Webb sees in infrared. It sees heat, it sees through the dust, and most importantly, it sees time. This is the concept that breaks most people's brains, so let's simplify it. Light takes time to travel. When you look at the moon, you are seeing it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun were to suddenly vanish, we wouldn't know for 8 minutes. We are always inextricably living in the past. But when you look at a galaxy that is billions of light years away, you're looking billions of years into the past. You're looking at the universe as it was before the Earth even existed. However, as that ancient light travels through the expanding universe, it gets stretched. It's like a slinky being pulled apart. The light waves get longer and looser, shifting from the blue and visible part of the spectrum down into the red, and eventually into the infrared. This is called cosmological redshift. The further back you look, the redder the light becomes. Hubble couldn't see this far infrared light. Its eyes weren't built for it. It was blind to the very beginning. Webb was built specifically to catch these faint, stretched-out photons that have been traveling for 13.6 billion years. It is a time machine, engineered to take us back to the first minute after the cosmic clock struck midnight. But building a time machine is not easy. In fact, it was nearly impossible. The story of Webb is a story of a 10 billion gamble that almost failed. This mission began as a dream in 1996 with a budget of just $500 million and a launch date of 2007. It was supposed to be a quick, cheap successor. Instead, it became a decades-long nightmare of engineering hurdles, ballooning costs, and political battles. By 2011, the project was so far behind schedule and over budget that the U.S. Congress moved to cancel it entirely. It was effectively dead. It took a massive mobilization of the scientific community and a complete restructuring of the project to save it. In 2018, NASA brought in Gregory Robinson as the program director. He's the man credited with turning a toxic culture of delays into a finely tuned machine, improving efficiency from 55% to 95%. But even with the best management, the physics were terrifying. To see the faint heat of the early universe, the telescope has to be cold, unimaginably cold. It operates at roughly minus 233 degrees Celsius, just 40 degrees above absolute zero. If it were any warmer, its own heat would blind it. To achieve this, the telescope needed a sunshield, a 5-layer tennis court-sized umbrella made of a material called Captain. This shield separates the hot side, which faces the sun and reaches temperatures hot enough to boil water, from the cold side, which stays frozen in eternal night. The temperature difference between the two sides of the shield is over 300 degrees, separated by nothing but 5 thin sheets of plastic. And here was the catch. The telescope was too big to fit in a rocket. The primary mirror is 6.5 meters wide. The standard rocket fairing is only 5 meters. So the engineers had to do something that had never been done before. They had to build the telescope like origami. It had to fold up to fit inside the Ariane 5 rocket. And then, once it was alone in space, it had to unfold itself. This brings us to the 29 days of terror. That is what the engineers called the deployment phase. From the moment the rocket left the launch pad in French Guiana on Christmas Day 2021 until the telescope reached its final orbit, everything had to go perfect. There were 344 single points of failure. A single point of failure means that if that one thing breaks, if a pin doesn't pull, if a latch doesn't release, if a cable snaps, there is no backup. The mission is over. The $10 billion observatory becomes the most expensive piece of space junk in history. Unlike Hubble, which orbits just 570 kilometers above the Earth, Webb was headed for Lagrange Point 2 LO2, a gravitational parking spot 1.5 million kilometers away. If Hubble broke, we could send astronauts to fix it. If Webb broke, it was gone forever. The team at the Space Telescope Science Institute in Baltimore spent those 29 days in a state of controlled panic, watching telemetry data, waiting for the confirmation of every motor turn. They were listening for the mechanical heartbeat of a robot a million miles away. Miraculously, it worked. The sunshield tensioned. The secondary mirror swung into place. The gold-plated hexagons of the primary mirror wings opened up and locked. The launch was so precise that it saved enough fuel to double the mission's lifespan from 10 years to 20. The golden eye was open. Then came the waiting. The telescope had to cool down. It had to align its mirrors with nanometer precision. But finally, on July 11, 2022, the world changed. President Biden unveiled the first image, known as the Webb Deep Field. It showed a patch of sky the size of a grain of sand, held at arm's length. In that tiny speck of darkness, Webb revealed thousands of galaxies. The image was beautiful, yes. It was sharper and deeper than anything Hubble had ever taken. You could see the gravitational lensing, the way the mass of galaxy clusters warped the fabric of space-time, magnifying the faint lights behind them. But for the astronomers, the beauty was secondary. They weren't looking at the shapes. They were looking at the data. They were looking at the red dots. This is where the detective story truly begins. This is where the standard model started to crack. Buried in that first deep field, and in the subsequent surveys like JWST, the JWST Advanced Deep Extragalactic Survey, scientists found galaxies that defied explanation. One of the most famous is a galaxy cataloged as JWST. To the untrained eye, it's just a red smudge. But to an astrophysicist, it is a monster. The data tells us that we are seeing this galaxy as it existed just 290 million years after the Big Bang. In the grand scale of the universe, that is seconds after birth. According to all our best theories, the universe at that age should have been a dark, foggy place, populated only by small, dim, chaotic clumps of gas and the very first short-lived stars. It should have been the cosmic dark ages. But JWST is not a dim clump. It is luminous. It is massive. It spans over 600 light-years. It is hundreds of times brighter than our models predicted. It is a fully formed galaxy, sitting in an era where only proto-galaxies should exist. Imagine finding a skyscraper in a village from the Stone Age. It doesn't fit the timeline. And it gets worse. When Webb used its spectrographs to analyze the light from this galaxy, breaking it down into a barcode of elements, it found oxygen. Oxygen is a heavy element. In the universe, the only way to get oxygen is to fuse it inside the hearts of stars, wait for those stars to explode as supernova, and spew that oxygen out into the cosmos to be incorporated into the next generation of stars. That process takes time, lots of time. Finding significant amounts of oxygen just 290 million years after the Big Bang implies that multiple generations of stars had already lived and died. This means the universe turned on much faster than we thought. It means the dark ages were not so dark. It suggests that star formation in the early universe was not a slow, gradual trickle, but a violent, explosive burst. Then there is the mystery of the little red dots. Webb has found a population of compact, red objects that are roughly 100 times more numerous than expected. At first, scientists thought these were just massive, overdense galaxies, which would have completely broken our understanding of how gravity works. Now, the leading theory is that we are looking at quasars, supermassive black holes that are actively eating gas and dust. As the material swirls into the black hole, it heats up and shines brighter than billions of stars. But this solution only creates a new problem. If these are black holes, they are too big. How does a black hole grow to millions of solar masses in such a short time? In the standard model, black holes grow by slowly feeding on gas. But there hasn't been enough time for them to eat that much. It's like finding a newborn baby that weighs 300 pounds. It defies the laws of growth as we know them. This has led to radical new theories. Some scientists are proposing direct collapse black holes. The idea that in the early universe, massive clouds of pristine gas didn't fragment into stars, but collapsed directly, catastrophically, into giant black holes. These seeds would have given the universe a head start, anchoring the first galaxies and driving their growth at breakneck speeds. This is the crisis in cosmology. It is not that the Big Bang didn't happen. Let's be clear. The evidence for the expansion of the universe is still rock solid. It is that the recipe for how the universe evolved after the Bang is missing some key ingredients. The timeline is crunched. The structures are too advanced. The universe was mature when it should have been an infant. We are standing at a crossroads. The old models are struggling to hold the weight of this new data. The tension between what we predicted and what we see is growing every day. And this is just the beginning. Webb has only been looking for a few years. It has 20 years of fuel left. So what does this mean for us? It means we are not latecomers to a dying, old universe. We are observers of a cosmos that was ready for life, ready for complexity, and ready for mystery much earlier than we ever dreamed. The universe didn't wait billions of years to get interesting. It came out of the gate, sprinting. We have found the body. We have analyzed the fingerprints, and now we have to reconstruct the crime. As we move forward into this video, we are going to dissect these impossible galaxies one by one. We are going to look at the cosmic cliffs where stars are being born today and compare them to the ancient monsters of the deep past. We are going to travel to alien worlds where Webb has detected the signature of water in the atmosphere. We are going to dive into the physics of the invisible. This is not just a story about a telescope. It is a story about us. It is about our need to know where we came from. It is about the audacity of a species that, stuck on a small rock, orbiting an average star, decided to build a golden eye to look God in the face. The data is streaming down from L2 right now, at 28 gigabytes a day. Every packet contains a potential revolution. The golden eye is open, and it is not blinking. The question is, are we ready for what it is going to show us next? Stick with me. The journey has just begun, and the further we go, the stranger it gets. Let's dive into the dark. 344. That is the only number that mattered. It wasn't the $10 billion spent, or the 25 years of development, or the thousands of engineers across 29 countries who had dedicated their lives to this moment. When the James Webb Space Telescope left the Earth, the entire endeavor, the future of astronomy, and the careers of an entire generation of scientists boiled down to that one terrifying figure: 344 single points of failure. If you are not an engineer, let me explain what that phrase means. In most complex systems, redundancy is the safety net. If one engine on a plane fails, you have another. If a computer server crashes, a backup kicks in. But a single point of failure is a mechanism with no backup. If it jams, if it snaps, if it fails to turn, the mission is over. There is no plan B. There is no workaround. The machine dies. The James Webb Space Telescope had 344 of them. If just one of those pins didn't release, or one of those latches didn't open, the most advanced scientific instrument ever built would become nothing more than the most expensive piece of space junk in history. To understand why NASA would take such a colossal gamble, you have to understand the physics of the problem. We wanted to see the beginning of time. To do that, as we discussed, we needed to catch infrared light that is incredibly faint and incredibly old. To catch that much light, you need a giant bucket. You need a primary mirror that is at least 6.5 meters wide. But here is the catch. The biggest rocket fairing we have, the nose cone of the Ariane 5 rocket, is only about 5 meters wide. Do the math. You cannot fit a 6.5 meter mirror inside a 5-meter tube. It is physically impossible. It is like trying to fit a king-sized mattress into a suitcase without bending it. And unlike a mattress, you can't just squish a beryllium mirror. It has to be polished to a precision of nanometers. So, the engineers were left with a choice: build a smaller, less capable telescope that fits the rocket, or do something that had never been done before. They chose the impossible. They decided to fold it. This is where the origami gamble began. They had to design an observatory the size of a tennis court that could collapse into a bundle the size of a school bus. Then, once it was alone in the void, a million miles away from human hands, it had to unpack itself. It had to blossom. This brings us to the second terrifying constraint: location. The Hubble Space Telescope orbits the Earth at an altitude of about 570 kilometers. When Hubble launched in 1990 with a flawed mirror, it was a disaster. But it wasn't a death sentence. We could send astronauts up on the space shuttle to fix it. We gave Hubble glasses, and it worked. Webb does not have that luxury. To work in the infrared, Webb needs to be cold, colder than the surface of Pluto. The heat from the Earth and the Moon would blind it. So we sent it to Lagrange Point 2, or LA2, a gravitational sweet spot, 1.5 million kilometers away, directly behind the Earth relative to the Sun. That is 4 times further away than the Moon. There is no space shuttle that can go there. There are no mechanics on call. If Webb opened its eyes and saw nothing but a blur, or if a wheel got stuck halfway through deployment, that would be it. Game over. This was the shadow that hung over the project for decades. It is why the budget ballooned from $500 million in 1996 to nearly $10 billion by launch day. It is why, in 2011, the United States Congress almost killed the project entirely. They saw a money pit. They saw a project that was billions over budget and years behind schedule, managed by a culture that seemed unable to deliver. It took a massive mobilization of the scientific community to save it, and a complete restructuring of the management team, led by Gregory Robinson, to turn the ship around. Robinson, a quiet but firm NASA veteran, didn't just manage a schedule. He managed the psychology of fear. He reduced the efficiency drag and got the team to focus on one thing, getting it right, because they would only get one shot. And finally, that shot came. Christmas Day, 2021. It feels poetic, doesn't it? While the world was unwrapping gifts, thousands of astronomers were sweating through their shirts, glued to screens showing a launch pad in French Guiana. The Ariane 5 rocket roared to life, piercing the equatorial sky. And in a moment of pure engineering brilliance, the launch injection was so perfect, so precise, that the telescope didn't have to use its own fuel to correct its trajectory. That single moment of precision doubled the mission's life. We thought we had fuel for 10 years. Because of that launch, we have enough for 20. But as the rocket faded from view, the cheering stopped. The easy part was over. Now began the 29 days of terror. For the next month, the telescope had to conduct a slow-motion symphony of robotic movements while cruising through the dark. The first hurdle was the solar array. It deployed automatically minutes after separation. We saw it on the camera, a glimmer of silver extending out. Webb had power. It wasn't dead. Then came the antenna. It swung out and locked. Webb could speak to us. But then came the monster, the sun shield. The James Webb Space Telescope is essentially 2 different machines living in 2 different universes. On the bottom, facing the sun, is the spacecraft bus. It is bathed in scorching sunlight, reaching temperatures of 85 degrees Celsius, hot enough to boil an egg. On the top, hidden in the shade, are the mirrors and the instruments. They sit in eternal darkness at minus 233 degrees Celsius, just 40 degrees above absolute zero. Separating these 2 worlds are 5 thin layers of Kapton, a material that looks like aluminum foil, but is tough enough to stop a bullet. Each layer is thinner than a human hair. They had to be pulled out from the folded structure and tensioned tight, creating a kite-shaped shield the size of a tennis court. This was the moment of maximum danger. The plastic sheets were fragile. If they snagged on a bolt, they could tear. If they didn't pull tight, the heat would leak through, and the telescope would be blind. The engineers had designed a system of pulleys and cables that looked like the inside of a grand piano. Dozens of motors had to fire in perfect synchronization to pull those cables. For days, the team at the Space Telescope Science Institute in Baltimore sat in a room, sending commands and waiting. They couldn't see the telescope. They could only look at the telemetry, graphs and numbers on a screen. Motor 1 active. Motor 1 complete. Motor 2 active. Imagine the tension. You have spent 30 years on this. You are watching a line on a graph. If that line goes flat, your life's work is gone. I want you to pause with me here for a second. Really put yourself in that room in Baltimore. Look at the coffee cups piled up on the desks. Smell the stale air of a room that hasn't been vacated in 48 hours. Look at the faces of the people around you, people who have aged with this machine. Here is a question for you. Would you have pushed the button, knowing that there are 344 ways this could go wrong, and only one way it could go right? Would you have the courage to send the command? We often look at science as a cold, logical procession of facts, but at its heart, it is a gamble. It is a wager of human time and resource against the unknown. We throw our most precious creations into the dark and hope they survive. It's an act of faith. I want you to tell me in the comments, if you were the mission director and you saw a sensor reading that looked a little glitchy, maybe just a bit of noise, would you stop the whole sequence and risk the delay? Or would you trust the machine and push through? Because that is exactly the choice they had to make, over and over again, for 29 days. Back in the dark, the motors turned, slowly, agonizingly. The layers separated, layer 1, layer 2. The vacuum of space acted as an insulator between them. The heat from the sun hit the first layer and bounced off. What little heat got through hit the second layer. By the time the energy reached the fifth layer, it had dissipated almost entirely. The telemetry came back green. The sunshield was tensioned. The observatory began to cool. But we weren't done. The telescope was still blind. The mirrors were still folded up, like the leaves of a drop-leaf table. The secondary mirror was next. This is a small, round mirror that sits out on 3 long boom arms in front of the main gold honeycomb. It is the most critical optical component. The big gold mirrors collect the light, but they bounce it all to this one focal point. If the secondary mirror doesn't deploy, you don't have a telescope. You just have a very expensive gold sculpture. The command was sent. The booms extended. They latched. The room in Baltimore let out a breath they had been holding for a week. Finally, the wings of the primary mirror, the iconic gold hexagon, is actually made of 18 smaller segments. The central column holds 12 of them, but 3 are on a wing to the left, and 3 are on a wing to the right. They had to swing out and lock into place to complete the honeycomb. On January 8, 2022, the final wing swung into position. The latches clicked. The James Webb Space Telescope was fully deployed. The origami had opened. The gamble had paid off. But the machine was not yet ready to see. It was physically intact, but it was optically a mess. The 18 mirrors were looking at 18 different parts of the sky. They were not acting as a single surface, and crucially, they were still too hot. For the next few months, the telescope drifted toward L2, letting the cold of deep space seep into its bones. This was the cool down. It wasn't just about waiting. It was about physics. Heat is just atoms vibrating. To see the faint heat of the first galaxies, the atoms in the telescope's mirrors had to stop vibrating. They had to become perfectly still. As the temperature dropped, the instruments started to turn on. First, the near-infrared camera, NIRCam. Then, the spectrographs. The engineers began the tedious process of alignment. They had to move each of the 18 mirrors by increments smaller than the width of a virus, tilting and curving them until 18 separate images of a single star merged into one perfect, brilliant point of light. When that first alignment image came down, a picture of a random star used for calibration, the scientists were stunned. They expected it to be sharp. They didn't expect it to be perfect. The optics were performing not just within specifications, but better than the most optimistic predictions. The background of the image, which should have been empty black space, was littered with galaxies, Even when it wasn't trying, Webb was seeing the deep universe. The 29 days of terror were over. The era of the golden eye had begun. The engineering miracle was complete. We had successfully put a time machine in the sky. But a time machine is useless unless you know where to look, and unless you can understand what you are seeing. The relief of the deployment was quickly replaced by a new kind of tension, the tension of discovery. The data that started streaming back to Earth was complex. It wasn't just pictures, it was spectra, barcodes of light that held the chemical secrets of the cosmos. And almost immediately, the telescope began to whisper things that shouldn't be possible. It pointed its mirrors at a patch of sky that Hubble had already explored, a place where we thought we knew the story. It looked past the stars we could see, into the fog of the early universe. And there, looming in the darkness of the cosmic dawn, it found something that made the astronomers freeze. The origami gamble had worked. The box was open. But what was inside was about to break our understanding of reality. We had built this machine to confirm our theories. We had built it to fill in the last few pages of the history book. But the universe, it seems, had a different ending in mind, or rather, a different beginning. As the first official science images were processed, hiding behind the closed doors of NASA, to be revealed to the president, the rumors started to fly. "It's too bright," they said. "There's too much stuff." We thought we were looking for the first lonely stars flickering in the dark. Instead, we were about to walk into a crowded room. The engineering story ends here, with the machine humming quietly in the cold void, 1.5 million kilometers from home. But the detective story, the mystery of the impossible galaxies, that is just beginning. Because when you build a machine to look back in time, you have to be prepared for the possibility that the past is not what you remember. You have to be prepared to find out that the universe you live in is stranger, older, and more alive than you ever dared to dream. The mirrors are cold. The guidance sensors are locked. The first photons from the edge of time are hitting the gold. Let's see what they have to say. To see the beginning of time, you must abandon your own eyes. That is the single hardest truth of astrophysics. For thousands of years, our species has looked up at the night sky, believing that if we just built a bigger lens, a wider mirror, or a taller tower, we would eventually see everything there is to see. We built observatories on mountaintops to escape the clouds. We launched the Hubble telescope into orbit to escape the atmosphere. We polished glass until it was smoother than a calm ocean. But we were hitting a wall that no amount of polishing could break. We were trying to watch the birth of the universe, but we were looking for it in a language that the universe no longer speaks. We assumed that the cosmos was static, a fixed stage where stars simply walked on and off. But the stage itself is moving. The stage is growing. And to understand why the James Webb Space Telescope is not just a camera, but a literal time machine, you have to understand the tragedy of light in an expanding universe. Light is a traveler. It is the cosmic messenger that carries the story of the stars to us. When you look at the moon, you are not seeing it as it is now. You are seeing it as it was 1.3 seconds ago, because that is how long the light took to cross the gap. When you look at the sun, you see it as it was 8 minutes ago. If the sun were to suddenly vanish, we would remain blissfully unaware, bathed in its warmth for 8 full minutes before the darkness arrived. This delay is the key. It means that looking out into space is identical to looking back in time. As we peer deeper into the void, we are peeling back the layers of history. We see Jupiter as it was 40 minutes ago. The nearest star, Proxima Centauri, as it was 4 years ago. The Andromeda Galaxy, as it was 2.5 million years ago, when early humans were just beginning to craft stone tools. It stands to reason, then, that if we just looked far enough, if we stared into the deepest, darkest patch of nothingness for long enough, we should see the very first light. We should see the moment the lights turned on. We should see the Big Bang itself. But we don't. When Hubble looked as far back as it physically could, it found only a fading, blurry silence. The universe seemed to simply stop. For decades, this was the frustration that haunted astronomers. We knew the baby universe was out there, but it was hiding behind a veil we couldn't pierce. The problem wasn't the telescope. The problem was the universe itself. Imagine a wave of blue light, leaving one of the very first stars born after the Big Bang. This light is energetic, bright, and vibrant. It begins its journey across the cosmos, heading toward where Earth will eventually be born. But as this little wave of blue light travels, something catastrophic happens to the road beneath it. Space expands. This is not just galaxies moving apart. It is the fabric of reality, stretching like a rubber sheet. As the space stretches, the wave of light traveling through it gets stretched too. Its tight, energetic blue peaks are pulled farther and farther apart. Think of a slinky. Imagine holding a compressed blue slinky in your hands. Now, slowly walk backward, pulling it taut. The coils stretch out. The tight spirals relax into long, lazy loops. In the physics of light, a tight wave is blue, and a stretched wave is red. By the time that ancient blue light has traveled for 13.6 billion years to reach us, the expansion of the universe has stretched it so violently that it is no longer blue. It is no longer yellow. It is no longer red. It has been stretched all the way out of the visible spectrum entirely and into the infrared. It has become invisible to human eyes. It has become invisible to Hubble. This is the cosmic slinky. This is redshift. And this is why we were blind. The history of our origins is screaming at us from every direction, but it is screaming in a frequency we cannot hear. We were standing in a library full of books, written in invisible ink, wondering why the shelves looked empty. This realization changed everything. It meant that looking redder is literally looking older. It meant that if we wanted to see the baby universe, we had to stop building telescopes that see visible light. We had to build a machine that could see the invisible. We had to build a machine that could see heat. I want you to pause for a second and really try to visualize this, because it breaks your brain if you think about it too hard. Imagine that the past isn't gone. Imagine that the light from the dinosaurs, or the light from the formation of the Earth, is still out there, racing away from us right now. If you could teleport instantly to a planet 65 million light-years away and look back at Earth with a super telescope, you would see the T-Rex walking around live. So here is the question I want you to answer in the comments. If you could build a telescope powerful enough to see back to any specific moment in Earth's history, to watch it play out like a movie, what moment would you choose? Would you watch the building of the pyramids? The moment the asteroid hit? Let me know down below. But the expansion of space is only the first lock on the door of creation. There is a second lock, one that is equally frustrating: dust. The universe is a messy place. It is filled with vast, billowing clouds of gas and dust, the remnants of dead stars and the nurseries of new ones. These clouds are incredibly beautiful. They are the pillars of creation, the Carina Nebula, the great swirls of cosmic geography that make for stunning screensavers. But to an astronomer trying to see the beginning of time, they are a nuisance. They are smoke. Visible light cannot penetrate these thick clouds. When visible light hits a dust grain, it bounces off or gets absorbed. It gets scattered. This is why, when you look at the Milky Way on a clear night, you see dark patches where the stars seem to be missing. They aren't missing. They are just hidden behind a wall of soot. The earliest galaxies, the ones we are desperate to see, are often shrouded in these cocoons of dust. Hubble looked at these clouds and saw opaque walls. It was like trying to take a picture of a forest fire through the thickest black smoke. You can't see the trees. You can only see the smoke. But infrared light is different. Infrared waves are longer. They are slippery. They don't bounce off the dust grains. They flow around them, like ocean swells moving around a piling in the water. Infrared light passes through the dust as if it isn't even there. To understand this, think of a firefighter entering a burning building. The room is filled with black smoke. He can't see his hand in front of his face. But if he puts on a thermal imaging camera, suddenly the room lights up. He can see the heat signature of the door frame. He can see the glow of the fire at the source. He can see the unconscious person on the floor. The smoke is transparent to the heat. That is what the James Webb Space Telescope is. It is the firefighter's thermal camera for the universe. It turns the opaque walls of the cosmos into glass. When you combine these two factors, the redshift that stretches ancient light into the infrared, and the ability of the infrared to pierce through cosmic dust, you realize that Webb is not just an upgrade. It is a completely different species of observer. This dictated every single choice in its design. It dictated the strange alien shape of the machine. Why is Webb made of gold? If you look at the primary mirror, those 18 hexagonal segments aren't silver like a bathroom mirror. They are coated in a microscopic layer of pure gold. This isn't for vanity. It's engineering. Silver and aluminum are great at reflecting visible light, but they absorb infrared. Gold is the opposite. Gold is 99% reflective in the infrared spectrum. It is the perfect material for catching the faint, stretched heat signatures of the early universe. Why does it look like a sailboat on a giant silver raft? That raft is the sunshield, a 5-layer kite the size of a tennis court. Because Webb is designed to see heat, it must be cold. Incredibly, impossibly cold. If Webb were warm, its own heat would glow in the infrared, blinding its sensors. It would be like trying to take a picture of a firefly while holding a spotlight in front of the lens. So, the telescope hides behind its shield, forever turning its back on the sun, the earth, and the moon. On the hot side, the shield cooks at 185 degrees Fahrenheit. On the cold side, just a few inches away, the mirrors sit in a permanent, freezing shadow at minus 388 degrees Fahrenheit, just 40 degrees above absolute zero. In this freezing silence, the gold mirrors wait. They wait for the tiny, stretched, exhausted packets of energy that have been traveling for 13.6 billion years. When a photon from the first stars hits that gold, it rings the bell. It tells us not just that something is there, but when it was there. This is the power we now possess. We have built a machine that cancels out the expansion of the universe. We have built a machine that erases the dust. And this brings us to the precipice of the mystery. Because we assumed that once we turned this time machine on, we would see the cosmic dawn as a gentle sunrise. We expected to see the universe slowly waking up. We expected to see tiny, clumsy baby galaxies just beginning to pull themselves together from the primordial gas. We expected a nursery. The standard model of cosmology, the recipe book we use to explain how the universe grew, was very clear on this. It said that in the beginning, gravity was weak and slow. It said that it took billions of years for chaos to organize into structure. It told us that if we looked back to just 300 million years, After the Big Bang, we would find a lonely, dark place with only a few scattered, dim protostars. Hubble couldn't prove this because Hubble couldn't see it. We were confident in our theories because we had no data to contradict them. We were comfortable in the dark. But then, the mirrors unfolded. The sunshield tightened. The instruments cooled down to their operating temperature of 40 Kelvin. The team at the Space Telescope Science Institute in Baltimore held their breath and pointed the golden eye at a patch of empty sky. They opened the shutter. They let the invisible light pour in. And when the first images appeared on the screens, the comfort vanished. The theories didn't just crack, they shattered. What Webb saw in the deep infrared was not a nursery. It was a metropolis. It saw galaxies that were too bright. It saw structures that were too big. It saw a universe that was fully formed, aggressive, and alive, existing at a time when it should have been nothing but a whisper. It was as if we looked into a crib, expecting to find a newborn baby, and instead found a fully grown adult staring back at us. The redness of the light confirmed the age. There was no mistake. These things were ancient. They were from the very dawn of time. But they were monsters. This is the aha moment that sent a shiver through the entire scientific community. We realized that by seeing the invisible, we hadn't just found a new way to take pictures. We had found a crime scene. The cosmic slinky had brought us a message we weren't ready to read. The dust had cleared to reveal a reality we hadn't predicted. The universe didn't wake up slowly. It seems to have been born running. This is where the story shifts from engineering to detective work. Because if the baby galaxies are this big, and this bright, and this old, then how did they get there? How do you build a galaxy in the blink of a cosmic eye? To answer that, we have to look at the first suspect. We have to look at the one thing in the universe capable of breaking the rules of physics as we know them. We have to look at the darkness itself. Webb was hunting for light, but what it found was a shadow that might explain everything. The mirrors are locked. The data is streaming down, and the impossible is about to become real. Let's not mince words. The model is broken. For decades, we comforted ourselves with a specific story about how our universe began. It was a safe, logical, and orderly story. We believed that after the violent expansion of the Big Bang, the cosmos entered a long, quiet slumber. We called this the Dark Ages. We theorized that gravity needed hundreds of millions of years to gently coax the primordial gas into the first fragile structures. We believed the first galaxies were small, messy, and dim. Cosmic toddlers stumbling in the dark, slowly learning how to be galaxies. It was a comfortable theory. It made sense. It fit the math. But the James Webb Space Telescope has looked into that darkness, and it has found something that shouldn't be there. It didn't find toddlers. It found monsters. When the first data from the JD's survey, the JWST Advanced Deep Extragalactic Survey, began to trickle down from Lagrange Point 2, the mood in the control rooms wasn't just celebratory. It was confused. The astronomers were looking for the faint, shy glimmer of proto-galaxies. They were hunting for the very first sparks of light in a universe that was supposed to be filled with fog. Instead, the sensors were overwhelmed by bright, massive, and confident beacons of light, shining from an era where nothing of that scale should exist. Imagine you are a doctor walking into a hospital nursery. You expect to see rows of bassinets, each containing a sleeping newborn, fragile, small, and just beginning their lives. Now, imagine you walk into the same nursery, pull back the blanket of a crib, and find a fully grown man, sitting up, reading a newspaper, and smoking a cigar. Your first reaction wouldn't be scientific curiosity. It would be panic. You would assume you had lost your mind, or that you were in the wrong room. You would question the fundamental laws of biology. Adults do not fit in cribs. This is exactly how astrophysicists felt when they analyzed the light from a galaxy now known as JWST 14. This collection of stars is located at a redshift of roughly 14. In human terms, that means we are seeing it as it existed just 290 million years after the Big Bang. In the 13.8 billion year lifespan of the universe, this is the blink of an eye. It is the very first moment of the cosmic morning. According to every simulation and every textbook written since the days of Edwin Hubble, a galaxy at this time should be a tiny, chaotic smudge of gas, barely holding itself together. But JWST 14 is not a smudge. It is luminous. It is massive. It spans over 6,600 light-years across. It is hundreds of times brighter than our models predicted for this epoch. And it isn't alone. Webb is finding these impossible galaxies everywhere it looks. They are too big. They are too bright. And most terrifyingly for the theorists, they are too old. The existence of these galaxies creates a paradox that strikes at the heart of the standard model of cosmology. We call this model lambda CDUMs. It is the recipe we use to bake a universe. It tells us exactly how much dark matter, dark energy, and normal gas you need to build a galaxy. According to this recipe, gravity is a slow worker. It takes time to pull cold gas clouds together until they are dense enough to ignite nuclear fusion. It takes even more time for those individual stars to gravitationally bind into a galaxy. To find a structure this massive, this early, implies that gravity somehow hit the fast-forward button. It suggests that the universe didn't wake up slowly. It woke up screaming. The gas didn't gently coalesce. It collapsed violently and rapidly, birthing billions of stars in a frenzy that defies our understanding of thermal physics. If these galaxies are real, and the data says they are, then our timeline of creation is wrong. The universe grew up fast. It was mature, aggressive, and fertile long before we thought it was even possible. We are forced to confront a startling possibility. The Dark Ages were never dark. They were likely a blazing fireworks display of cataclysmic proportions that we are only just now beginning to see. I want to pause here for a moment, because this feeling, this mixture of confusion, and awe, is rare. We live in an age where we think we have the answers. We carry the sum of human knowledge in our pockets. But right now, you are witnessing science getting broken in real time. So, I have a question for you to consider. When you hear that the standard model might be wrong, that our fundamental understanding of the universe's history is being rewritten, how does that make you feel? Does it make you feel anxious? Like the ground is slipping out from under you? Or does it make you feel excited to know that there is still magic left in the dark? Pause the video for a second, look inward, and let me know in the comments. Are you Team Crisis or Team Adventure? Because the mystery gets deeper. It's not just about how big these galaxies are. It's about what they are made of. Remember, Webb isn't just a camera. It is a spectrometer. It doesn't just take pictures. It tastes the light. By stretching that infrared light into a spectrum, that barcode of reality we discussed earlier, Webb can identify the chemical fingerprints of the elements inside these distant objects. When scientists pointed Webb's spectrometer at JWST 14, they expected to see a pristine, primitive chemical signature. The first stars in the universe should have been made of only two things, hydrogen and helium. These were the only elements created in the Big Bang. There was no carbon, no nitrogen, no iron, and certainly no oxygen. Those heavier elements, what astronomers call metals, can only be forged in the nuclear hearts of dying stars. You need a star to live its entire life, fuse hydrogen into heavier things, and then explode as a supernova to scatter those elements into the cosmos. Then, the next generation of stars forms from that enriched gas. It is a cycle that takes millions upon millions of years. It is the slow, grinding evolution of the periodic table. So, when Webb tasted the light from this infant galaxy, it should have tasted only hydrogen and helium. It didn't. The spectral lines spiked. The data screamed. Webb detected significant amounts of oxygen. Let that sink in. Oxygen? The very stuff you are breathing right now. The element that requires generations of stellar life and death to produce. Finding oxygen in a galaxy just 300 million years after the Big Bang is like finding a fossil of a dinosaur in a rock layer that dates back to before the Earth was formed. It breaks the chronology. The presence of oxygen implies that JWST 14 isn't a first-generation object. It implies that entire civilizations of stars had already lived, burned furiously, and died in spectacular supernovae before this galaxy was observed. It means that the universe had already gone through multiple cycles of birth and destruction in the time we thought it was just getting started. This fundamentally shifts our place in the narrative. We used to think that the early universe was a hostile, sterile void, and that the ingredients for life, carbon, oxygen, nitrogen, were latecomers to the party, appearing billions of years later. But Webb is telling us that the cosmos was chemically ready for complexity almost immediately. The ingredients for life were being cooked up in these monster galaxies while the universe was still in its infancy. This revelation has sent theorists scrambling back to their whiteboards. How do you form stars that fast? How do you make them die that quickly? Some astrophysicists are proposing direct collapse scenarios. They suggest that in the dense, hot soup of the early universe, giant clouds of gas didn't bother breaking up into individual stars. Instead, they collapsed directly under their own weight to form massive stars, titans thousands of times the mass of our Sun, that lived for only a few million years before detonating. These Wolf-Rayet stars would be the cosmic equivalent of heavy metal drummers, living fast, dying young, and trashing the hotel room of the galaxy with heavy elements. But there is another suspect in this cosmic whodunit, a suspect that might explain why these baby galaxies are so impossibly bright. As Webb continued its survey, it began to notice something else peculiar. Scattered among the monster galaxies were hundreds of tiny, compact objects. In the visible light, images from Hubble, they were invisible. But to Webb's infrared eyes, they glowed with an intense, piercing heat. They were small, roughly spherical, and incredibly red. Astronomers have affectionately dubbed them little red dots. But don't let the cute name fool you. These objects are breaking the models just as badly as the monster galaxies. The prevailing theory is that these little red dots are not normal galaxies at all. They are the hiding places of supermassive black holes. We usually think of black holes as the end of the story, the drain at the bottom of the sink. But in the early universe, they might have been the architects. The data suggests that these compact red objects are actually baby galaxies being powered by voracious black holes, quasars, that are consuming gas at a rate that borders on the impossible. When a black hole eats, it doesn't just disappear the matter. The gas swirling into the drain heats up. It glows with the brilliance of a billion suns. If these little red dots are indeed black holes, they are overmassive. In the modern universe, a black hole is usually a tiny fraction of its galaxy's mass. But in these early objects, The black hole might be almost as heavy as the galaxy itself. This leads to a terrifying conclusion. The black holes might have formed first. Standard theory says you build a galaxy, and then some stars collapse to form a black hole in the middle. Webb is hinting that perhaps the black holes were the seeds, giant primordial black holes formed directly from the collapse of the Big Bang's plasma, and their immense gravity pulled the rest of the galaxy around them. They were the anchors. The monsters in the nursery weren't just the galaxies. They were the beasts lurking in their centers. This changes the cosmic dawn from a sunrise into an explosion. It paints a picture of an early universe that was violent, energetic, and crowded. It wasn't a slow fade in. It was a sudden, blinding flash of activity. The light from JWST to Rewrote has traveled for 13.5 billion years to reach the golden mirrors of the telescope. It has stretched and tired along the way, shifting into the infrared. But the message it carries is fresh. It tells us that we have underestimated the universe's capacity for creation. We thought we were observing the first tentative steps of a universe learning to walk. Instead, we found footprints of a giant that had already been running for miles. The implications of this are staggering. If galaxies were mature at 300 million years, if oxygen was already abundant, then the timeline for potential life in the universe must be pushed back by billions of years. We often wonder if we are late to the party, if we missed the golden age of the galaxy. But Webb suggests that the party started before the invitations were even sent. The crisis in cosmology isn't a failure of science. It is the growing pain of a species that is finally opening its eyes wide enough to see the truth. The universe is not a static, predictable machine. It is a dynamic, wild, and incredibly efficient engine of complexity. But if the galaxies are this big, and the black holes are this massive, there is one more piece of the puzzle that doesn't fit. If you have monsters in the nursery, you need to feed them. You need fuel. You need dust. And that brings us to the most beautiful and confusing paradox of all. Because where there is fire, there must be smoke. And Webb has found that the early universe, which should have been transparent and clear, was actually choking on dust. How do you create a dust storm in a vacuum? How do you fill the void with soot before you've barely lit the first fire? To answer that, we have to look away from the monsters and look at the ghosts. We have to peer into the cloudy veils of the pillars of creation to understand what happens when a star dies and how its ashes become the seeds of the next world. The detective story continues. We have found the body. We have identified the suspects, but we still don't know the motive. Why did the universe rush? What was the hurry? As we command the telescope to pivot, the gears turn in the cold silence of the L2 orbit. The sunshield shimmers, protecting the instruments from the blinding heat of our own star. We are turning our gaze from the distant past to a place much closer to home, yet equally mysterious. We are about to look at the death of a star in high definition. And in the debris, we might just find the answer to the mystery of the beginning. The monsters in the nursery were just the warning. The dust is the evidence. And what we are about to see in the heart of the nebula will change the way you look at the dust under your own bed. The universe is dusty, and that dust is you. But before we can understand the dust, we must understand the wind that blows it. The cosmic winds are rising, and Webb is the only sail we have. We were lied to. Not by the scientists, not by the history books, and certainly not by the telescope itself. We were lied to by the light. For decades, we operated under a comfortable assumption that light equals mass. If you see a smudge in the deep universe that glows with the intensity of a billion stars, You assume it is a billion star. You assume it is a massive, fully formed galaxy. When the James Webb Space Telescope first opened its golden eyes and peered into the abyss of the cosmic dawn, it saw hundreds of these bright red smudges. They were everywhere. Oh, they were too big, too bright, and too numerous to exist so soon after the Big Bang. They broke our models. They threatened to rewrite the laws of physics. They made us think the universe was impossibly mature, a fully grown adult standing in a delivery room. But the universe wasn't mature. It was wearing a mask. We call them the little red dots. It's a deceptively cute name for what might be the most terrifying objects in the history of creation. These aren't the gentle nurseries of star formation we hope to find. They are monsters. And investigating them has revealed that our story of how the universe began is not a story of slow, gradual growth. It is a story of violent, ravenous hunger. To understand why this discovery sent a shiver through the spine of the astronomical community, you have to understand the panic that set in during Webb's first year of operations. As the data streamed down from L2, the graphs plotted a nightmare scenario for cosmologists. We found galaxies existing just 500 million years after the Big Bang that appeared to be more massive than our own Milky Way. Think about the absurdity of that. The Milky Way took billions of years of mergers, cannibalism, and star formation to grow to its current size. These ancient galaxies shouldn't have had the time to eat enough gas to get that big. It was like finding a toddler who weighs 300 pounds. It didn't make sense. If these measurements were accurate, then our understanding of gravity, of dark matter, and of the Big Bang itself was fundamentally flawed. We were facing a crisis in cosmology. But science is a detective story. And in a detective story, you never trust the first alibi. The astronomers looked closer. They stopped looking at the pictures and started looking at the spectra. This is where Webb stops being a camera and starts being a forensic laboratory. By passing the light of these little red dots through its near-infrared spectrograph, Webb broke the light apart into its component rainbows. This is how we fingerprint the cosmos. If those dots were made of stars, the rainbow would look a certain way. A smooth continuum of light, broken by the distinct signatures of stellar atmospheres. That is not what Webb saw. Instead of the soft glow of billions of stars, the spectra screamed. They showed broad, violent emission lines, signatures of gas, moving at incredible speeds, thousands of kilometers per second. Stars don't move that fast within a galaxy. Stars are heavy. They drift elegantly in orbit. The only thing that can whip gas around at those velocities, heating it until it outshines an entire galaxy, is a gravitational well of infinite density. A black hole. This was the wolf in sheep's clothing. These objects weren't massive galaxies filled with stars. They were tiny, compact baby galaxies, runts of the litter, that were harboring a terrible secret. Inside them sat supermassive black holes that were disproportionately huge, devouring gas with such ferocity that their burps of radiation were brighter than the galaxy itself. We were looking at a flashlight and mistaking it for a bonfire. This realization solved one problem, but immediately created another. It saved the standard model of cosmology because it meant those impossible galaxies weren't actually that massive. They were just incredibly loud. We didn't have to throw out the Big Bang, but it introduced a mystery that is, in many ways, far more unsettling. If these little red dots are powered by supermassive black holes, we have to ask, how did the black holes get there? In the local universe, the quiet, modern cosmos we live in today, black holes are the tombstones of stars. A massive star lives its life, burns its fuel, and collapses. It leaves behind a black hole maybe 10, 20, or 30 times the mass of our Sun. To get a supermassive black hole, one that is millions or billions of times the mass of the Sun, that seed has to eat. It has to merge. It takes eons. But Webb is showing us supermassive monsters existing when the universe was less than 1 billion years old. There simply wasn't enough time for a dead star to eat its way to that size. It's like trying to fill a swimming pool with a teaspoon in 5 minutes. The math doesn't work. This forces us to confront a radical idea. What if these black holes didn't come from stars? What if they didn't have to wait for a star to live and die? Before we dive into the abyss of that theory, I want you to pause for a moment. We are talking about the destruction of matter on a scale that defies comprehension, happening in the dark ages of the past. Here is a question for you to consider. We often think of black holes as the villains of the universe, cosmic vacuum cleaners that destroy everything they touch. But if these monsters were present at the very beginning, outshining their host galaxies, is it possible they are actually the heroes? Could it be that without these seeds of destruction, the structure of our universe would never have formed? I want to know your take. Are black holes the architects of life, or the inevitable end of it? Let me know in the comments below. Now, let's go back to the nursery. The existence of these little red dots supports a theory that was once considered fringe: direct collapse. Imagine the early universe. It is not the cold, empty vacuum we know today. It is a thick, hot soup of hydrogen and helium gas. In the standard story, this gas cools down, clumps together, and ignites to form the first star, population 3 stars. These stars are huge. They burn fast. They die. And then they make black holes. But in the direct collapse scenario, the gas clouds are too massive and too hot to form a star. They are so dense that gravity overwhelms the pressure of the gas before fusion can even ignite. The cloud doesn't turn into a star. It simply fails. It collapses under its own weight, bypassing the star stage entirely, and crunches directly into a singularity. This creates a heavy seed, a black hole that starts its life not at 10 solar masses, but at 10,000 watts or even 100,000 solar masses. This explains the little red dots. They are the children of these heavy seeds. They were born big, and they were born hungry. This changes everything about how we view our origins. We used to think of the early universe as a pristine, quiet place where galaxies slowly assembled like Lego bricks, piece by piece, with black holes appearing much later as a symptom of aging galaxies. Webb has shown us that the universe was born with a heart of darkness. The black holes were there from the start. They were the anchors. Their gravity was likely the glue that held the first proto-galaxies together. They pulled the gas streams in, churning the cosmos, heating the surrounding matter, and regulating the birth of stars. The wolf in sheep's clothing wasn't an intruder. It was the shepherd. When we look at those little red dots now, we don't see them as errors in the data. We see them as the engines of creation. They are quasars in training. As they feed, they blast out jets of radiation that clear away the fog of the early universe, ionizing the neutral hydrogen and effectively turning on the lights of the cosmos. This recontextualizes the cosmic dawn. It wasn't a gentle sunrise. It was a violent, chaotic eruption of energy. The seeds of chaos were sown early, and from that chaos, order began to emerge. But there is a catch. If these little red dots are indeed the seeds of all modern galaxies, it means that at the center of our own Milky Way, the dormant giant Sagittarius A, the black hole that quietly sleeps in the center of our galaxy, was once one of these ravenous monsters. It means that billions of years ago, if you had looked at the Milky Way from a distance, you wouldn't have seen a spiral of stars. You would have seen a little red dot. You would have seen a blinding crimson eye staring back at you. We are the survivors of that gluttony. We are the dust that didn't get eaten. Webb has peeled back the layer of deception. It has shown us that the impossible galaxies were an illusion caused by active black holes. But in doing so, it has revealed a universe that is far more dynamic and dangerous than we imagined. And yet, the mystery deepens, because if these black holes are eating the gas, they are also processing it. They are spewing out heavy elements. They are mixing the cosmic cocktail. We have found the engines. We have found the seeds of chaos. But engines need fuel, and seeds need soil. What was the universe made of in those first moments? Was it just hydrogen and helium? Or was the chemistry of life already brewing in the cauldron? To answer that, we have to stop looking at the monsters and start looking at the ghosts. We have to look for the invisible signature of the one thing that connects the burning quasar to the blood in your veins. We have to look for carbon. The little red dots have told us how the universe grew, but they haven't told us what it grew into. As Webb turns its sensors toward the faint, ghostly traces of the first chemicals, we are about to discover that the ingredients for life might not be a modern accident. They might be as old as the monsters themselves. The chaos is just the beginning. The chemistry is the key, and the key is hidden in the smoke. The universe was not supposed to be ready for you this early. Carbon is the anchor of your biology. Oxygen is the breath in your lungs. Iron flows through your veins. For a century, the standard model of cosmology taught us that these precious heavy elements were late arrivals to the cosmic party. Complex ingredients forged slowly, painfully, over billions of years in the dying hearts of ancient stars. We believed the infant universe was a barren, sterile wasteland of simple hydrogen and helium, a cold and lonely place, incapable of supporting complex chemistry, let alone the building blocks of life. We thought we were the result of a lucky accident that could only happen after the cosmos had aged into maturity. We were wrong. The James Webb Space Telescope has looked into the smoke of the cosmic dawn, and it did not find a blank canvas waiting for the paint to dry. It found a masterpiece that was already finished. The house wasn't being built while we waited outside. It was furnished, heated, and stocked with the ingredients for life before the first galactic structures had even settled into place. The void was not empty. It was fertile. To understand why this changes everything, you have to stop looking at the pretty pictures. You have to look at the light itself. When the Webb telescope points its golden hexagonal mirrors at a target like JWST, it does something far more profound than just taking a photograph. It acts as a time machine, yes, but also as a prism. Through an instrument called NIRSpec, the near-infrared spectrograph, Webb takes the faint, ancient light that has traveled for 13.5 billion years and breaks it apart. It stretches that light into a rainbow of data. To the untrained eye, this data looks boring. It looks like a jagged line on a graph, a series of peaks and valleys that you might scroll past without a second thought. But to an astronomer, that jagged line is a crime scene photograph. It is a DNA test. Every element in the universe absorbs light at a specific, unique wavelength. Hydrogen leaves a specific fingerprint. Carbon leaves another. Oxygen leaves a signature that cannot be faked. When the scientists at the Space Telescope Science Institute saw the spectrum for JWST, the room didn't erupt in cheers immediately. It fell into a confused, stunned silence. The data was screaming something impossible. This galaxy is located at a redshift of roughly 14. That means we are seeing it as it existed just 290 million years after the Big Bang. In the grand scale of cosmic time, this is milliseconds after the starting gun. This is the era we call the Dark Ages, a time when the universe should have been shrouded in a fog of neutral gas, with only the very first tentative stars flickering on in the gloom. Theory predicted that these first galaxies should be tiny, faint clumps of pristine gas, innocent, simple, and chemically pure. But JWST 14 worms is not faint, and it is certainly not innocent. It is bright, shockingly bright. It spans over 1,600 light-years, a fully formed structure that dwarfs the theoretical predictions for this epoch. But the size isn't the thing that keeps astrophysicists awake at night. It's the chemistry. Webb's spectrograph detected strong, undeniable signatures of oxygen. Let that sink in for a moment. Oxygen is not a primordial element. The Big Bang didn't make oxygen. The Big Bang made hydrogen, helium, and a tiny pinch of lithium. To get oxygen, you need a star to be born. You need it to fuse hydrogen into helium for millions of years. Then, you need it to run out of fuel, collapse, and heat up enough to fuse helium into carbon, and carbon into oxygen. Then, and only then, does that star have to die. It has to explode in a supernova to scatter those new heavy elements out into the cosmos, where they can clump together to form the next generation of star. This is a cycle that is supposed to take time. It is a slow, grinding process of stellar evolution. Finding significant amounts of oxygen just 290 million years after the beginning is like walking into a nursery and finding a newborn baby reading Shakespeare. It implies a maturity that simply shouldn't be there. It means that the first stars we are looking for, the legendary population 30 stars, must have lived fast and died young, with a violence and efficiency we can barely comprehend. These weren't the gentle giants of our current theories. They were monsters. They must have burned through their fuel at a gluttonous rate, exploding in cataclysms that enriched the surrounding gas with heavy metals almost immediately. The universe didn't wait billions of years to start mixing the cosmic cocktail. It started bartending the moment the lights came on. And it gets stranger. Alongside the oxygen, Webb is sniffing out carbon. It is finding dust. In our previous chapter, we talked about the smoke obscuring the monsters. Now we know what that smoke is made of. It is made of the same stuff as you. This discovery forces us to rewrite the timeline of habitability. We used to think that for the first few billion years, the universe was hostile to life because the ingredients simply didn't exist. You can't build a cell without carbon. You can't have water without oxygen. We thought we were safe in assuming that the early universe was a dead zone, a construction site where the raw materials were still being manufactured. But the fertile void suggests otherwise. It suggests that the ingredients for life were present almost from the very start. The universe was awash in the chemical building blocks of biology when it was barely out of its infancy. The table was set, the fire was lit, the chemistry was bubbling in the cauldron, while the cosmos was still hot from the Big Bang. This creates a profound shift in how we see ourselves. We often feel like latecomers to the universe. We look up at the stars and feel small, insignificant, a fleeting accident that occurred after 14 billion years of silence. But Webb is showing us that the potential for us, the chemical potential for eyes and hearts and brains, has been woven into the fabric of space for as long as the stars have been shining. The implications for life elsewhere are staggering. If the ingredients were available this early, then the window for life to emerge isn't just the last few billion years. It is the entire history of the universe. Rocky planets, water, organic chemistry. These things could have formed eons before the Earth was even a glint in the solar nebula. We are looking at a universe that wanted to wake up. The Dark Ages were not dark. They were a frenzy of creation. The little red dots we discussed earlier, those compact galaxies powered by ravenous black holes, were not just destroying, they were churning. They were the engines that circulated these heavy elements, blowing the oxygen and carbon out of the galaxies and into the intergalactic medium. They were seeding the void. So when you look at that deep field image, don't just see the pretty lights. See the history of your own atoms. The oxygen in the breath you just took might have its origins in a star that died 12 billion years ago. But the story of that oxygen begins here, in the fertile void of the dawn. We are not separated from these ancient galaxies by time. We are connected to them by substance. The iron in your blood is the same iron that Webb is hunting in the spectrographs of the deep past. We have found the engines. We have found the fuel. We have found the smoke. And now, we realize that the smoke is the signal of a universe that was never truly empty. This brings us to the edge of the map. We have pushed the timeline back as far as we can go with our current understanding. We have seen the galaxies that shouldn't exist, and we have tasted the air of the infant cosmos. But there is one final mystery that Webb is teasing, a mystery that lies even deeper than the first stars. If the universe was this mature, this fast, what happened before the first light? We are approaching the limit of what light can tell us. We are staring into the true unknown, where the laws of physics themselves might begin to fray. The fertile void has given us the ingredients, but it hasn't given us the recipe. How did the universe organize itself so quickly? What is the invisible scaffolding that held these impossible galaxies together? The answer might not be in the light we can see, but in the darkness we can't. We have to talk about the invisible hand that guides the stars. We have to talk about the ghost in the machine that makes all of this structure possible. We are done looking at the shiny ornaments on the Christmas tree. It is time to look at the tree itself. The next chapter of this story isn't about what glows. It is about what pulls. It is about the heavy, silent, invisible matter that outweighs everything else in the universe, 5-1. We are about to turn the telescope toward the shadows. But before we take that step into the dark, I want you to pause and look at your hand. Look at the complexity of your own skin. If the universe had the ingredients to make you within the first 300 million years, why did it wait 13 billion years to do it? Or did it? Are we the first to wake up in this fertile void? Or are we simply the first to look back and notice the house was ready all along? This is the question that the James Webb Space Telescope has placed in our laps. It is no longer a question of physics. It is a question of destiny. The data is there. The oxygen is there. The stage was set. Were we late? Or are we just the latest? I want you to take a moment and answer that question for yourself in the comments below. Do you find it comforting or terrifying that the universe was ready for life so early? Does it make you feel more connected to the cosmos or more lonely? This journey is far from over. We have analyzed the chemistry and we have marveled at the impossible galaxies. But the biggest twist is yet to come. The universe isn't just fertile, it's distorted. The very space we are looking through is warped. To understand the beginning, we have to look through a lens made of gravity itself. We have to look at the dark matter. If you want to see what lies in the shadows, make sure you are subscribed and have the notification bell turned on. You are not going to want to miss what Webb sees when it turns the lights off. Welcome to the fertile void. Now, let's see what's hiding in it.